So we're going to talk about 4.5, linearization, and then as an offshoot of linearization, Newton's method and differentials. So an important idea in calculus is that differentiable functions are what we call locally linear. And to try to illustrate that, let's compare two functions, sine x and x to the 2/3 around x equals 0. So sine x is differentiable. And if you look at a little region around 0, if you were to zoom in with your calculator enough, you would see eventually a little piece of this is going to look very much like a straight line. That's what we mean by locally linear, that if you zoom in enough, it's going to look like a line. And of course, the line it's going to look like is going to be its tangent line. Now, at a place where it's not differentiable, like at this cusp, no matter how much we zoom in there, it's never going to look like a line. It's always going to have this point to it. And so there would be no good way of trying to approximate this curve around this area using any kind of a straight line. So in the blue, we see our definition of a linearization. If f of x is differentiable at x equals a, then the equation of the tangent line, which now we're going to use some fancy notation, L of x equals f of a plus f prime of a times x minus a, defines what's called a linearization of f at a. So that's kind of a language that may not be real familiar. The approximation, that is approximating f of x using this tangent line, L of x, is the standard linear approximation of f at a. And the point x equals a is called the center of the approximation. So to try to illustrate what's happening and get this notation so it doesn't look so out of the blue, as it were, if you imagine, here's your point x equals a, then on the curve there, since it's on that function, that y value would be f of a. So that point that's on the curve right here would be a comma f of a. We know that the slope of the tangent line at that point would be the derivative, f prime, evaluated at a. So the tangent line, which would use that point and slope, would be y minus the y coordinate, which is f of a, minus, or equals rather, the slope, which is f prime of a, times x minus a, the x coordinate. If we add the f of a to the other side, then we're going to see this is exactly what we called in the blue paragraph up there, our linearization. So this is exactly our linearization. So all I have done is then called that using functional notation L of x. So essentially what linearization is just using a tangent line. And we're going to use it for a couple of different things, to approximate the value of the function and then some offshoots from that. So let's look at the next screen. So here is an example. We have f of x is equal to the square root of 1 plus x. We're going to make our linearization at the point x equals 0. And then we're going to use that linearization to approximate the value of the function at a little different place away from 0, but not very far away from 0. So to find a linearization, we're just finding an old idea, a tangent line. So our point is going to be, we're going to plug in 0 into our function. 1 plus 0 is 1, square root of 1 is 1. So our point is 0, 1. Extra convenient because that's actually the y-intercept. Now the slope, we know, is going to be the derivative evaluated at 0. So first let's find the derivative. So that's sort of a chain rule derivative. 1/2 times 1 plus x to the negative 1/2 times the derivative of the inside function, which is just 1. So we'll evaluate our f prime at 0, because that's where we're trying to find that tangent line, is that when x is 0. So this 1 over 2 times 1 plus x to the negative 1/2 is really just 1 over 2 times the square root of 1 plus x. When we plug in 0, we get 1 plus 0 is 1. Square root of 1 is 1, times 2 is 2. So we're going to get just 1/2. So there's our slope. We have a y-intercept. So our tangent line is going to be y equals 1/2 x plus 1. This is what we're referring to as our linearization. Nothing earth-shattering about that. Now what we're going to do is use this to approximate the value of the function. This is the idea of linearization. Because we kind of know what the graph of this looks right? We know square root of x, and then the x plus 1 is going to translate at 1 to the left. So we're talking about a square root of x function there. And so we're taking this derivative at 0, and we're saying that this tangent line is going to be a reasonable approximation to this red curve as long as we don't go very far away from where we found the tangent line. And so we can see that to get to 1.02, our x value is going to be 0.02. 0.02. So that's what we're going to plug into our function. So we're finding, to find L of, we're going to call it 0.02, because remember, our f of x was 1 plus x. So the x that we need to get to the square root of 1.02 is going to be just the 0.02. So using our tangent line, we'll take 1/2 of 0.02 plus 1. So half of 0.02 is 0.01. So that makes our approximation. We're going to say that f of 0.02, that is the square root of 1.02, is approximately 1.01. Pretty painless to find since we're just using a tangent line, a line, to approximate this curve, that square root curve. So let's just get some notation and some vocabulary in here. Here's our approximation. Now we want to compare it to the actual value so we can talk about the error, the relative error, and the percent error. These are ways that we compare it to the actual value. So you can break out your calculator for a moment here. The actual value, what we're going to take as the actual value of the square root of 1.02 is just what our calculator gives us. So, and that's still just an approximation, but it's going to be better than our tangent line approximation. So when I plug it in, I'm getting like 1.009950. It goes on and on and on. I'm going to leave it up on the screen. So the error is going to be the difference between the actual value, what our calculator gave us there, and our approximation, the 1.01. So I'm going to say it's 1.01 minus that 1.00995, on and on and on. So I'm going to go, when I do that, what I'm getting is mine's in scientific notation, 4.9506 times 10 to the negative 5. So I think that's going to be a decimal point, 4 zeros, and then 495. And there's more, but I'm just going to round it off right there for now. So that's our actual error. So you can see we're really close. Our approximation is really close. Of course, we didn't go very far away because we only went 0.02 away from x equals 0. And the curve that we're looking at isn't really all that curvy. It's a pretty slow bending curve there. So that matters. So the relative error, we're going to take the actual error and divide it by the actual value of the function. So I'm going to take, and I'm going to not use the rounded values, but I'm going to take that actual error and divide it by the actual value of the true value of our function, which we're using our calculator's best approximation. So we'll use our calculator skills and not do the rounded answers, but take that calculator version of square root of 1.02, the difference rather, the 0.000495, on and on, divide that by the 1.00995, on and on. And what I'm seeing there is I'm getting in scientific notation again, 4.90182 times 10 to the negative 5. So I'm going to call that 0.0000, and then it's like 490, and on and on and on. So that's the relative error. And then our percent error is we just change that relative error to a percent by moving the decimal over a couple places. And you can see it's really, really accurate because we're less than 0.005%, from the actual value. Anyway, that's the idea of using a linearization, a tangent line to approximate the value of the function. Now, another use for this linearization idea is we can use what's called Newton's method, which is, I don't know if this is exactly what our calculator uses when we do the calculate zero. If it isn't the exact version, it's pretty close to this. So it's a way of using a tangent line to approximate where a function crosses the x-axis. So what we do is we imagine that here's the zero we're trying to find, that yellow dot. So we pick a point, we make a guess, somewhere over here. So I'm going to say there is our guess. And then we put that up there. Here's the visual. We look at the tangent line to that curve. And so we can find that tangent line fairly easy. We extend that tangent line until it crosses the x-axis. We find that value and we say that is going to be our next approximation. That x sub 2 that I just wrote there is going to be our approximation to our zero. And then we're going to repeat the process. So then we're going to take our, I'm trying to find a color that I can use and they don't mess it up. So now we're going to run this point to the curve and we're going to find the tangent line to the curve there and extend that until it hits the x-axis, find that zero, and we just keep going and going. And what happens is, in most cases, it homes in there pretty quick and gets us a really good approximation to that zero. So here's how it's going to look. We start with our guess, which is that x1 comma f of x1 that I have written there in yellow. So we do our tangent line. So our slope there, the slope is going to be f prime evaluated at x1. So that makes our tangent line y equals f of x sub 1. And then that's going to be plus f prime of x sub 1 times x minus x sub 1, our first guess. So there's our tangent line. Now imagine that's that red line that we drew over there. We're going to follow that red line and we want to find out where does it intersect the x-axis. Well, it intersects the x-axis when y is 0. So we plug in 0 for the y, and then what we want to do is solve for that x. That's going to be our next guess. That's going to be what we have called our x sub 2. So to do that, we're going to subtract that f of x sub 1 to the other side. So now that's moved over. Then we're going to divide by the f prime of x sub 1. That's going to move that over. And then we're going to add that x1 to the other side. And so we're going to get that. And that will leave us this x, which I'm going to call x sub 2, the next approximation. So what we get is then that x sub 2 is going to find this number that we talked about on the graph, and then we're going to iterate it again. And so what we'll do then after that is our x3, this is just going to repeat itself, is going to be x sub 2, just bumping up one, minus f of, not f prime's on the denominator, f of x sub 2 over f prime of x sub 2. We keep doing this, and so our Newton's method formula becomes the next guess is going to be the previous guess minus f of that previous guess over f prime of the previous guess. That is our formula for what we're going to do for Newton's method. And of course, using our calculator, it gets really easy to do this really fast. So I'm going to bump to the next screen. And here is our example. We're going to find the zeros of this function. And I'm going to rewrite here again. Remember, x sub n plus 1 is going to be x sub n minus f of x sub n over f prime of x sub n. So what I'm going to do on the calculator to make this really efficient is we can put into y1 our function. So we'll put in that f of x. And then into y2, we're going to plug in our derivative, f prime of x. So I'm going to do that, and I'm going to pause the video for a minute so I can get my calculator set up, then I'll rejoin you here. Okay, so mine's all set up. I have that x cubed plus 3x plus 1 in y1 and 3x squared plus 3 in y2. Now, if you graph that, you can see that the function is going to cross, it looks like somewhere in between -1 and 0. So we can just make a guess, and it doesn't really matter how close we are unless our function is really pretty severe, like it's got some vertical asymptotes. So just so we can do this together, I'm going to choose the first guess to be a -0.3. Now, to do this really efficiently on our calculator, once we've entered our function as y1 and our derivative as y2, we can type into our calculator -0.3, the -0.3, store that, so the store button is there right above the on button, then hit the x button, the x comma t comma theta comma n button, and then hit enter, and it will store that value -0.3 in as the x, and so it'll just repeat it again. Now we can do something like what we see right here on our calculator version. So we can go x minus, and then we're going to take the function is going to be our y1 of x. Remember, these x's are all right now the -0.3 divided by, and then we can go y2 of x. And then before we hit the enter, if you store it as x, it will tell the calculator to take this thing we just computed and replace what we did have, that -0.3, by what the result is of this. When you do that, what I'm getting is a negative 0.3222324, on and on and on. Now once we have done that, we have kind of queued it up on our calculator and set it almost like programming it. So if you hit enter, it will replace that process. It will replay that process. It'll do it all over again with our new stored value of x. And so this one I'm going to call x2. Then what I'm getting for x sub 3 is -0.322185. Now, what we can see is that whatever decimal places we get in agreement, I guess just the -0.322, we know these are going to be correct where we have agreement. So I'm going to hit enter again. And so now I'm getting the fourth iteration, x sub 4, and the first one was just a guess. The fourth one, I'm getting -0.3221853, and I can see the one above it, and all of these agree with what I'm seeing on the previous one. And then the next one, the next digit there on this one is going to be a 6, whereas on the one before that, it was actually a 5. So we can know that we have accuracy, so we know that whatever this settles into be is going to be 5 or bigger. So we could get 1, 2, 3, 4, 5, 6, 7 decimal places of accuracy, and we would round that and say -0.3221854 is going to be accurate to those 7 decimal places. So that's Newton's method. Now, just a couple of heads ups. Sometimes things can go wrong, but not terribly often. One is because we have in our formula up here, because you see f prime of x sub n is in the denominator, if we make a guess and it leads to us trying to divide by a derivative that's 0, that isn't going to work. But that's not a major issue. That would just mean go pick a different first guess and see where that leads you, and probably it will steer you away from that place where the derivative is 0, and you're just going to be fine. In the green, we can see that if this converges, if Newton's method converges, you know you can have 100% confidence that that is a 0 of our function. Where the tricky part comes in, if you have something with vertical asymptotes, like imagine a tangent curve, and if you're trying to find a 0 and it happens to be close to that vertical asymptote, you have to be sometimes very careful on your first guess. If you're not, it may send you careening off somewhere, and you may still find a 0, but it may not be the 0 that you're trying to get, the one you're looking for. So sometimes you have to be pretty careful about what your first guess is. And the other thing that can happen is, and this one we don't have a good fix for, it just may not work, is if it starts to either bounce back and forth or it starts careening out and getting bigger and bigger and bigger instead of closing in on a single number. So what's happening sometimes in this kind of loop is if you make your first guess here and the curve isn't behaving the way we really need it to, I'm going to try to visualize this. So the tangent line comes in here, and we find our x sub 2 here. And then we go to the curve, and we find a new tangent line. And now this tangent line comes through, and it sends us right back to where we started. And so when this happens, you can just end up going back and forth, back and forth, back and forth between two numbers and never close in on anything. And if you use a cube root of x, and it'll actually do even worse than that. It'll start sending you to a bigger positive, then a bigger negative, then a bigger positive, and it won't close in to find that 0 at 0. But those don't happen very often. Okay. Let's talk about differentials. This is another application or use of linearization. So some background first in the white. F prime of x equals dy dx is notation. So we just have two different notations for that same idea of a derivative. It was never really intended. Leibniz came up with this dy dx notation. It was never really intended to be a quotient of two numbers, but to represent that limit as f of x plus h minus f of x over h goes to 0, that delta y over delta x as delta x goes to 0. But if we do define dx and dy as variables, we just have to make sure that we can get back to dy dx equals f prime of x and not do too much crazy stuff with it. So in yellow we see a definition. Here's our definition of these now differentials. So if f of x is differentiable, then we choose dx to be an independent variable. We can make it be whatever we want, and the differential dy is going to be f prime of x times dx. You can see that's just doing the algebra with our derivative up here. So all we did was say dy dx is equal to f prime of x, and then multiply that dx to the other side, and that's what led to this expression. So we say then that dy, that differential dy, depends on f prime of x and dx. So dx is the independent variable, and then dy we got to find. So here's the idea. Find in the green, we're going to first just do one that's pretty much straightforward. Find the differential dy and evaluate dy for sine 3x when x is pi and dx is negative 0.02. So we'll start by taking the derivative dy dx, and the derivative of sine of 3x is going to be cosine 3x, and then with the chain rule times 3. We'll multiply the dx to the other side, so we'll get our differential dy is 3 cosine of 3x times the differential dx. Then we'll plug in our numbers, so dy is going to be, we're going to get 3 cosine of, and when you plug in pi, that's going to be 3 cosine of 3 pi, and that's going to be times our differential dx, which is going to be a negative 0.02. So that makes our differential dy. Since the cosine of 3 pi is negative 1, That's going to be negative 3 minus, or I guess that's a times, rather, times negative 0.02. And so that's going to be a positive 0.06. That's our differential dy. Okay, now moving on to an idea of what we might do with a differential. So we can use then these differentials to kind of approximate what we're going to call delta y. So in our diagram over here, we can see that we have our function y equals f of x is the yellow. The green value x is a point on that curve. We've drawn the red tangent line to the curve at that point. So we imagine now that we're going to move over a delta x from where we started. And what we would like to know is how does the value of the function change as it moves from x to x plus delta x. That is, what is this delta y, the change in y? So what we're going to do is use our tangent line to approximate that change in y, that delta y. So what we're going to do is know that our slope, because dy dx is equal to f prime of that x, that point, and that's the slope, then we're going to see that this distance right here, that's the change in y on the tangent line, that's dy, and this, we're going to say, choose dx to equal delta x. So then what we're going to do is say dy, that differential, which when we multiply that dx to the other side, we're going to use this dy to approximate the delta y. So you can see from the picture, the little red dy is not exactly the same as the blue delta y, but as long as that delta x doesn't get too big and we stay pretty close to where we're getting the tangent line, that'll be a decent approximation. That's the whole idea, is to approximate that change in y. So let's do an example here. And so let's say that we have the area is pi r squared. And what we're going to do is choose our, let's estimate using differentials the delta area, that change in area, if r increases, our radius increases from 10 to 10.1 centimeters. So what we're seeing here now is we're changing the radius a little bit. So our delta r is that 0.1, and we're going to make that equal to dr. Now we're going to approximate the delta area. How does this change in our radius? As we increase the radius from 10 to 10.1, how does that affect that area? And so we're going to approximate that change in the area, that delta area, using the differential dA. So with our function here, we're going to take its derivative. So just doing calculus, the derivative of a with respect to r is going to be 2 pi r. We're going to multiply our differential dr to the other side, so it becomes the differential dA is equal to 2 pi r times the differential dr. Now we've got numbers for these, so we can say this differential dA, which remember we're going to use to approximate the change in the area, that is going to be 2 pi times, and we're going to use the original radius, that nice one, 10, times the dr, which was equal to the delta r, which is the 0.1. And so that is going to be, let's see, the 0.1 times 10 is just 1, so that's going to be 2 pi. I'm sorry, not dr, that's dA. So we are saying that when our radius changes from 10 to 10.1, we're going to approximate that change in the area. We're going to approximate that with our dA, which we're saying is 2 pi. Okay, that's the idea behind it. Let's see our next screen here. So here we're trying to figure out how accurately should we measure r, the radius of a sphere, if we want the surface area to be within 1% of the true area. And the surface area of a sphere is given by the formula 4 pi r squared. So let's think a little bit about what we know and then what we're going to try to go with this. So if we want our true area to be within 1% of the actual area, if we want the measured area to be within 1% of the true area, then we want our percent error to be less than 1%. That means we want our relative error, if you remember how we did this earlier, to be less than 0.01. Now remember, the way we got the relative error was we took our differential, in this case we're talking about relative error of the area, so we took our differential dA over the actual area A, and that's what we got to be less than 0.01. So we want that dA over A to be less than 0.01. That's kind of what's driving this. And we want to know then what's that impact on the R. What does that tell us about how accurately we are going to need to measure R? So using the same idea, we want to figure out what percent error in measuring R, the radius, will lead to a percent error of less than 1% in the true area. So what we're going to do is we're trying to find what is dr over r, so that we can then make that into a percent to say what percent accuracy do we need in the measurement of the r, the radius. So how much error, this is representing that dr is representing the error in measuring the radius, and the dA is measuring the error in computing the area given our potentially flawed measurement of the radius. Okay, there's the background. So we're going to differentiate this, so we'll take dA over dr, the derivative of area with respect to the radius is going to be, and now we just differentiate this and get 8 pi r. We're going to multiply the dr to the other side, so here's our 8 pi r dr. Now, here's where we're going to use this idea here. We know that dA over A we want to be less than 0.01. So what we're going to do is divide both sides by A, and the area we said was 4 pi r squared, and we know we want that to be less than 0.01. You with me there? So now this is progress because we can cancel the pi's. We can cancel 4 with the 8 and get 2. And so now what we're getting is 2. Oh, we can cancel one of the r's also. So we're getting 2 times dr over r. We want to be less than 0.01. Follow that? So now we can divide by the 2. So what we're saying is we want the relative error in measuring the radius to be less than, and when you divide 0.01 by 2, it's going to be 0.005. So this tells us how much accuracy we need in measuring the radius. That's a relative error, and we can convert that to a percent and say it's going to be 0.5%. So if we need to measure our area, surface area of a sphere within 1% accuracy, we're going to have to find a way to measure our radius within 0.5% accuracy. All right, very good.